Good afternoon, everyone, and welcome to the Singapore Science Centre and our Iron Science Competition 2007. Now, the Iron Science Teacher Competition was inaugurated in 2005 as an activity of the International Year of Physics. The Science Centre continues to organise this event as a part of its mission to inspire science and technology, teaching and learning. With the continued acknowledgement and recognition of the Ministry of Education, we hope this annual event will become an important venue where teachers can exchange ideas on teaching science and inspiring science learning in their pupils. The winner will be pronounced the Iron Science Teacher of 2007 and will enjoy a special learning journey to the National Science Learning Centre at York in England to attend a course in science teaching and communication. This very special opportunity is generously provided by British Council Singapore, which has also contributed souvenirs to all contestants and judges. Let's show our appreciation to the British Council for their generosity and support. Now, please allow me to invite our Assistant Chief Executive of Education Programs, Associate Professor Prof. Lim Teck Ming.
Well, on behalf of the Science Centre, I want to welcome each and every one of you to come and witness this annual contest, Iron Science Teachers Competition. As you heard from Florence, this is third year in the running. And what you're seeing today is the first part of the competition. Tomorrow there's going to be the second part. Okay, so all the contestants will be kept in suspense as to whether they will be the grand champion or not. Probably from later your reaction, we might get some hint whether we have some winners among them. Okay, well, I shan't take up too much time. I mean, you're not here to look at me, and I'm here actually to also serve as a judge. I'm just welcoming you on behalf of the director who is not free today. But if you come tomorrow, he'll be here to give the official welcoming address. Okay, well, we thank British Council once again for the partnership, and we thank the judges for helping us out with this. So now I'll just pass the time back to Florence, and I think the contest will start very soon. Right? We are ready.
Thank you, Prof. Lim. Now, let me introduce to you our distinguished panel of judges. We have with us Prof. Lim Teck Ming, who is also the Vice Dean of Science from the National University of Singapore. We have Ms. Eileen Tan, Regional Coordinator, East Asia, British Council of Singapore. Ms. Aw Sok Heng, Senior Curriculum Specialist, Science Branch, Curriculum Planning and Development Division, Ministry of Education. And Ms. Alice O. Lin, Master Teacher, S7 Cluster, Schools Division, Ministry of Education. Now let's show appreciation for their kind interest in our event being here today. Now before the contest proper begins, let me briefly explain the rules. Now as mentioned before, the contest is open to all teachers in all local and international schools, to all trainee teachers of the National Institute of Education, and to all academic staff of all institutes of technical education. Contestants need not be science teachers, but they must give a short lesson demonstration on a science topic of their choice. Each presentation must be in English. So what's so special about the Iron Science competition? Now, contestants must create a captivating lesson based on the items in the list of secret ingredients which were made known to them only a week ago. Now, another set of items only made known to the contestants an hour ago this very afternoon is also available for their use. Now, all materials they use in the lesson demonstrations are provided, so they cannot over-prepare. They cannot make teaching aids or training aids, and their lessons and lesson planning is therefore very important. Now, each contestant has 1 minute to set up, immediately followed by a total of 6 minutes to present, and to field any questions from the judges and you, the audience. Now, we advise that the contestants finish their presentation within 4 minutes to leave more time for Q&A, as the effect of their presentation on the audience is important in consideration of the judging process. We therefore encourage you to ask questions during the Q&A period. Now, it's important to give feedback to the teacher on the learning process also. Now, significant minutes are marked by the sound of a bell. and the timekeeper will sound the bell as such. The first bell will mark the start of your presentation. The next bells will be sounded at 4 minutes and 5 minutes into the presentation, and double rings are lastly sounded on the 6th minutes. The contestant must end his or her presentation immediately and leave from the front of the auditorium. Okay? There will be a short 15 to 20 minute recess at about 3:30. Refreshments will be provided just outside the auditorium. Now, after all the contestants of this session have shown their best, the judges will retire to deliberate for about 20 to 30 minutes. Their decisions will be carried over to tomorrow afternoon's session, when the eventual Iron Science teacher of 2007 will be determined. Now, the judges will comment also on the performance in general or specifically before we end today's session. So before the fun begins, let me introduce the secret ingredients that we have. We have a foam cup, a wire clothes hanger, a toothbrush, and some leaves. Okay, without further ado, let's have our first contestant, and she is Miss Lim I Ping from Millennia Institute.
Hi, good morning, class. 1 minute setup, right? Okay, let's start. Now, previously we have studied the quantitative part of kinematics, which is the calculation. And today we are actually going to do, for this lesson, we are actually going to do the qualitative part, which is the explanation part. Okay? Now, let's think of this as, now you all have heard of Romeo and Juliet, right? How they committed suicide and all that. So now, let's say instead of drinking poison as they did in the play, this is the Juliet, like me, very light as a feather. This is Romeo, heavier, okay? And they decided to jump off HDB flat in Singapore, okay? Alright? Now, wait, sidetrack. I'm not trying to say I approve of suicide, alright? Suicide is actually the easy way out. Only cowards commit suicide. Living is hard. Presenting in front of a group of people is hard, alright? Dying is so easy, okay? Now, back to physics. If I have these two, Romeo and Juliet, jump off from, let's say don't jump, let's say initial velocity is 0, they drop off from the top of the building, who will hit the ground first? Okay, think first, this is a trick question, so think. There are 3 possibilities. A, B, and C. Okay, as in they hit the ground. Who will hit the ground first from the same height, from the same initial velocity of 0? Now I'm not going to give you the height of the HDB flat. I'm sure you can calculate from what we have learned last lesson. But now I just want you to think about the motion qualitatively, right? Given one, I'm trying to have 2 different mass. One is very small mass, one is much heavier mass, right? Which one will hit the ground first? The boat will hit the ground first. Okay, how many in the audience, how many in the class agree with her? Quite sure, it's very good. So nobody believes that the leaf, alright? Okay, let's do it. Can I? Okay. Don't worry, I do this all the time in class, nothing happens. Alright? Okay, what happened? What happened? Can I put it separate? Yes, I can. But when I put it separate, the common sense, not common sense. But actually, okay, like I say this is a trick question. Why did I put the book together with the leaf? And what happens when I put them apart? Okay, when I put them apart, okay, now quickly, no time. Obviously, the book will hit the ground first. Okay, the leaf will take longer. Why? Why? Yes, thank you. Okay, yeah. I think now inquiry based, supposed to make your thing first, but no time, every time got to finish syllabus. Okay, alright, so air resistance, very good. Okay, now, but the thing is, the moment I put the leaf on top of the book, I actually try to remove the air resistance in the sense that, do you notice they both fall at the same rate? They didn't separate out. The leaf didn't fall slower than the book. They fall together. They actually fall together. The leaf fell together with the same with the book. So no matter what's the mass, things falling under Earth gravity will fall at the same rate of 9.81. Very good. 9.81 meter per second square. Okay? Thank you.
Are there any questions that you'd like to ask, I think?
Bring this whole thing into falling vacuum.
How will I bring this whole thing to falling into vacuum? Usually when we exclude air resistance, there is the idea of vacuum. But because vacuum is not something that they see in their everyday life, when I try to link to vacuum, it's harder for them to see. So I try to use concrete stuff to link to the abstract concepts. So telling them this will happen in vacuum doesn't really work, not unless they really have a chance to see it happen in vacuum. Actually, what I usually will do is, if I have a video clip of things falling in vacuum, that's what I will show, more as a concrete way of presenting the concept. So, okay, thank you.
Okay. Next, we have Madam Goh Lee Teng from Sealing Primary School.
Good afternoon, everybody. Can I have a show of hand? How many of you have actually accidentally bumped into somebody and you felt a pain on your arm? Okay, alright. That concept, I have also come across it, especially when I go shopping with my husband. Because we always bump so close to each other such that we feel a sharp sensation at one part of our arm, and that we define it as static electricity. Okay? Okay, what is static electricity? Basically, it is a situation where electrical charges are produced on the surface of a material. Okay? And this is actually produced especially when objects are rubbed against each other's surfaces. So what I'm going to show you today is I have the toothbrush together with the styrofoam cup, okay, and I'm going to show you how it can actually move the leaves, okay, just a little bit, right, to show the movement, because static charges are actually produced when surfaces are rubbed, and this charge can actually be transferred to the leaf which is placed on the table. Alright, so I need you to observe really very, very carefully on the rubbing effect. Can't project this through the visualizer. Can you see the leaf moved just now? Okay, maybe I'll show you using another object, the clothes hanger, which is one of the secret ingredients as well. Did everybody see it just now? Yeah, okay, I'll show you one more time. I'm sorry, but I think there's some problem with the surface that of the materials that I'm using. Can I invite any questions from those who have Any questions?
Do you think it'll work better if you like crumble the cup into bits and use that to
Because I was just afraid that I couldn't do anything to disturb it, yeah.
Do you think that
But actually I tried it with a toothbrush and it did work, but just at the surface of the toothbrush is a bit rough, more rough than this, yeah.
do you think that it failed with the leaves because the leaves are moist?
It's a bit heavy, I would say, because I tried with a smaller leaf that's lighter, yeah.
Maybe you can tear out the pieces of paper into smaller pieces.
Yeah, I intended, but because of the time limit, that's why I actually prepared it at the side. But because this is one of the secret ingredients, so I wanted to use it because I tried, yeah, paper will actually be a better idea. Okay, thank you.
Okay, morning everybody. Just a background knowledge. Today I'm starting a lesson for Sec 1, mathematics lesson. It's on quadrilaterals. Okay, so I've titled it the quadrism 4. Okay, I'm sure before you all come to Sec 1, you all have learned something about quadrilateral. So may I pose a question to you? Can you name me some examples of quadrilaterals? Anybody? Let's give me one example. Oh, yes.
Square.
Oh, square. Okay, very good. Any others? Quadrilaterals that you know? Wow, you already have read the textbook. That's good. Okay, so square, rectangles. Okay, today I'm going to just tell you a story and also introduce a few more quadrilaterals to you. Okay. Okay, let me introduce this family of 4. Okay, but this family of 4, they are rather quarrelsome. Okay, first, this is Papa square. Okay, then Papa square is fair, all sides are equal, and big, muscular, angular, right? Then I have Mama parallelogram, a bit more shapy, okay, right? And these parents, they have 2 kids. The elder son is a rhombus who takes a little bit of, looks like the daddy, okay, 4 sides equal, and also a bit shaped like the mama. And they have a younger child, which is the trapezium. Now this is the problem kid. She feels that she is the oddball, doesn't really look like the daddy or the mommy. Okay, now this family lives in a little village and they are happily living together. They thought that they are the only shape around them because they are not introduced to the rest of the world. And this oddball, just don't like the rest and always think that she's out of place. And basically, they quarrel about anything, okay, because the quadrism 4. Okay. Now, one day, Daddy heard about the shape fair and decided to bring his family to have fun, to have some family time together. Okay, so Daddy, where's my daddy? Okay, so Daddy and Mommy, okay, brought the 2 little children to go for this shape fair. Now, when they first stepped into this shape fair, they realized and they noticed that there are other things with other shapes. Like this one looks a bit like oval. This is a heart shape. And they also saw the happy families of trees, having fun at the fair. And they also saw other shapes having fun as well, right? So basically at the fair, they saw they saw shapes enjoying themselves, sitting on a seesaw, trying to balance each other. And for the first time, they are introduced to different shapes, different other shapes beside their shapes with 4-sided, right? And then they learned to appreciate each other's uniqueness because every shape has its own properties, every shape has its own purpose, and they learn also to appreciate others' shapes around them and to accept each other's differences as well. So Ever since then, they decide to live happily ever after. As for the properties, I'll introduce more in the next lesson. Thank you.
You tell us what to do with the other one. Who is the friendly one? Foam or leaf?
Oh, the form of leaf. The form of leaf is more of a environmental friendly, actually planned for some argument between the styrofoam and the leaf. The styrofoam is more environmentally harmful because when you heat it up, it gives off the toxic film, and then the leaf is more biodegradable. So I actually planned for an argument between these two. Yeah, but I'm more comfortable with the shapes. Yeah.
Okay, I'm ready.
Okay, you may begin.
Good morning, class. Last lesson, I taught you about forces, right? Today, this lesson, we are going to extend a little bit more. But before I begin the lesson, I want to tell you a love story. Alright? Once there was a very beautiful lady. She's very fair. Alright, she's styrofoam cup. And there are 3 suitors going after her. Oh, they love her so much. They love her so much. They are secret admirers. However, the boldest is the toothbrush. He says, I will get her heart. The heart is of course inside the styrofoam, right? I will get her heart. So he tried something. He tried soft talk. But too soft, he can't get into the cup. He can't get into the cup. Oh, but before I carry on, I must let you know that they have same amount of love for this cup. I don't know how you measure love by percentage or whatever units. However, just take note that, they have a same amount of love for this cup, okay? So love represents the force. Remember force I taught you the last lesson? Force I'm applying is always the same, okay? Force represents the love. So he used the love. Oh, he can't enter the styrofoam cup. Then you think, maybe soft talk doesn't work. Let me try a harder talk. I love you. I love you, I love you. Oh, it still can't enter her heart. So he was a bit sad. He gave up. And here come the box. And the box thinks that, you have a smaller surface area. I have a bigger surface area. It is not about soft talk or hard talk, It is about your surface area. I can surely get into her heart. You watch and see. Are you sure? Just watch. And so, the box came and he said, oh, my sweet little fat lady, I'm sure I can get your heart. And he started talking and whatnot. So he tried to use his surface area, which is larger than the toothbrush. He tried and tried. He tried. He can't enter as well. Oh no, he is disappointed too. And actually, they're all so disappointed, these two. And quietly, the clothes hanger is an introvert. He loved her so much, but he just wouldn't say. He just waited and observed what's going on. And these two, they tried so hard, they get so fed up. They say, cut! Fed up, so the tone changed, not so loving. Cut! What else do you want? We have assured you of our love. All kinds of surface area and all. What else do you want? What trouble do you have that you can't love us? And you think I'm not mature enough? Am I not squarish enough? What else do you want? And actually, the cup said, as much as I want to love you, but I have a struggle. I can't trust men. Somebody has assured me before of his love, but he broke my heart and he broke off. How can I trust you? And suddenly this clothes hanger has a bright idea. Bing! He knew what is going on in the heart of the cup. And one day the clothes hanger came. And the clothes hanger told the cup, my fair lady, I know exactly what you need. And listen to what I've said. But first take a look. I'm different from the rest. I have a super small surface area just over here. Oh yes, I see it. What's so very different than the rest? Oh, and I want to tell you something. I heard the knot in your heart, and I want to assure you of my love, just like the rest. But more than that, I want to tell you something. Here, please. Oh, let me find my ear, please. Sorry, I forgot to do it.
And the clothes hanger say, my dear, you cannot trust any man. Though I'm a man too, but really you can't trust any man. Your future does not lie in the hands of any man. Your future lies in the hand of the Almighty God who loves you. And I love God. And I'm going to trust God that He's going to help me to be faithful and to love you. And as he is saying, as the clothes hanger is saying, he used his small surface area, the word that is sharper than any double-edged sword. And the clothes hanger spoke into the life. Where was it? Oh, it dropped out already. The clothes hanger spoke to the life of the styrofoam cup, and he got the heart of the styrofoam cup. And they live happily ever after. Oh, I'm so happy that you're so happy for the clothes hanger. But class, that's not just a love story, you know. I told you, is it over? Okay, I told you that, I taught you about force, right? Actually, this love story relates to this, okay? Pressure is equals to force over area. Remember, there's the same amount of love. So I hold the force the same. I didn't cheat when I press this against this, when I press this against this, and I press this against this, I'm using the same amount of force. Trust me or not, later you can try it during recess time. Okay? So the force is the same, but the surface area is different. You realize who got into the heart of the cup? Who? Hanger. The surface area was the smallest. You're right. If this is the smallest, this will be the pressure will be the largest. Mathematically, we know that, right? Okay, so this love story, I hope you will remember and you will relate, it's inversely proportional. Alright, next time, maybe you can think a story for me, okay, to how to relate, what's the relationship between the force and the pressure. Alright, that's all. Thank you. Question and answer time? Any questions? Yes. Oh, that one, right? Oh, I forgot that one. So actually, I plan to have the leaf and the cup. Okay. Then they will fall. And actually, I tried, it worked, but the storyline doesn't sound very good. So actually, because I believe that storytelling is important to capture the hearts of the students especially. And romance BGR, is what teenagers are into. Oh my goodness. It's okay. So actually, you can actually put a blue tack, and if you tilt each blade a little bit, I hope I don't break it, tilt in the same direction. But I don't have a blue tack here. But if you put it, it can actually twist down, but it's not enough weight now. So it can spiral something like that, nicer than that. So it can actually talk about dancing in the air, and the leaf will be part that can't dance, and this one can dance better, and this will win the competition. Something like that. Any other questions? Right, if you are curious, this is a true story. It's actually, I can't open, I don't mind. It's actually, is it videotape? Then I won't say. I won't say it's videotape, I won't say. It's just within the 4 walls I'll say, okay, I won't say, that's all. Okay,
Thank you, Mrs. Tay.
Yes, that's all.
Thank you.
Okay, good afternoon everyone. I'm Nazir, and today I'm going to present to you to a Sec 1 topic of flexibility. Now, to the one who just come in from Sec 1, in our Sec 1 classes, I've always shown this to them, and this is an object, a leaf, alright, and can someone tell me what state of material are these two objects on? It's a solid, right? Now, however, this solid is able to bend easily, while this solid takes up a bit more effort to bend it. Now, why is this so? Can anyone tell me why this is so? Alright, for this I'll need 4 volunteers. Can the 4 students up there please come down? Can you give them a round of applause, please? Okay, I need you to line up straight facing the audience. Okay, there's 4 of you. This is Ernest, this is Andrew, Sinfeng, and Geraldine, probably my students in 4 and T. Alright, now, if it's the leaf, okay, and these are particles of the leaf which are interconnected together, then what happens is, from each particle to another, there's a connection through this intermolecular link, and that is represented by, can you guys do hold out your hands and go to the front, don't come to the back, go to the front, hold out your hands together and hold each other now. Hold each other now. That's right, okay, hold hands. Now, when I start bending over here, and if I start bending over here, what you do is you start to move forward, and you move forward a little bit more, and you move forward a little bit less, unless you keep quiet over there. You stay there, alright? Now start bending over there. Okay, come on. Geraldine, move forward. Okay, you move forward too, and then you move forward. Okay, and if I bend backwards, what will you do, Geraldine? You'll come back. Okay? Now I'm going to push it a bit forward. I'm going to bend it a bit more now. Okay, you got to move forward further. Yeah, and you come back. You come back when I bring it back. Okay? Alright, now. Okay, put your hands down now. Okay? Now, what about a hanger? Why is it so difficult to bend it all the way down? Now, the difference between the hanger and the leaf is that the molecules here are a lot stronger. Okay, in the sense that you guys now don't hold hands, you guys interlock yourself. Okay, come on, I want you guys to see yourself interlocking each other. Okay, come on. Okay, so now when I try to bend it, Geraldine, you try to go to the front. Okay, since when you try to go to the front, you find it a bit more difficult, isn't it? It's a bit more difficult. That shows that the interlinked forces are a lot stronger between one another, between each particle. Alright? Okay, now, we've not rehearsed this, now I'm going to test you guys on something. What about the bristles of a toothbrush? It's easy to bend them. How would you arrange yourself? Would you stretch your hands out, or would you lock each other up? Fantastic. Alright. Okay, give them a round of applause now. Okay? Alright, thank you very much. It was on flexibility. Thank you. Are there any questions?
If a student asks you about the intermolecular bond, how would you
Yes.
explain?
The intermolecular bond?
When you say that they all link together.
Okay. Can you guys hold each other's hands as well? This would be the bond that represents them. This bond would represent them. If I were to tell my student what I would do if I may, and this may be a bit nasty, if I were to peel a part of the leaf out, what I'll be doing is using a scissors, and I'll be cutting this blue out. So the intermolecular bonds are gone. So he'll be representing one part of the leaf, and the remaining part of the leaf is still remained by them. Yeah. Okay, thank you very much then.
Thank you, Nazir.
Right, good afternoon everybody. Well, I've been a science teacher for the last 15 years and I always believe that science has to have some purpose, alright? Why do we teach concepts and why do we teach knowledge? That it must be applied sometime in our lives, in our daily lives, sometimes when we are, in some state of emergency. So I'm going to start off with telling you a story. Let's say you are going somewhere and you have lost all your friends and somehow they've gone somewhere else, or you have decided to go somewhere else, and you've not brought a water bottle with you, all right, and you've been walking for miles and you've been looking for some water to drink, and you come across a cliff, so you're already standing at the edge of a cliff, all right, and you don't see any more water source, but nearby you do see a rock, all right. And coming down the rock is just a single stream of water. Alright? Now this cliff is very close by, but it is not as close for you to reach out for the water. So what do we do? Alright? So this is where I say some of the concepts that we learn in the classroom, we need to apply them. Alright, so when you're going around and walking around, perhaps, alright, when you're going camping, you do have a toothbrush with you, and perhaps even a hanger with you, alright? If not, you just have to rely on nature. Alright, so I'm going to demonstrate to you how you can actually use these things to reach out for the water, and that's the whole purpose. Alright, so I'd like to have some volunteers quickly to come down here. Anyone? Even from this side, quickly. Time is essence. show you, all right, how this piece of leaf, a single leaf can be used, all right, in order to reach out for the water there. So pretend I'm here, and that's the cliff. So you're going to hold on to, you can hold on to the cup. And I can actually put it, all right, so this is where I am. So you're holding on to the leaf, and this is where the stream of water is. So I'm going to demonstrate to you, maybe you're not right at the table, just put it here. All right, so we're going to see how, you put it down there. You see how the water is going to flow towards you. Right? Remember, it's a single stream of water, and that's how you're going to reach out. But life is not that simple, isn't it? All right? So let's see how else, all right? If the distance is going to be a lot, larger than that, so what can we do? Perhaps you can go out for the hanger, right? Let's try it out, whether this works. Okay? So you're going to stretch this hanger towards the stream of water. If you try this out, it didn't quite work just now, but we will do that. The aim is to get some water into the cup. Is there any water getting into the cup?
To some extent, yes. A little. Couple of drops.
Couple of drops, okay. Well, if you do it long enough, I think there'll be some water for you to drink, right? Well, then again, right, sometimes you're not going to be that lucky in a camping trip. You may not even find anything. What you might just find is a branch. All right? So this is a branch, and how are you going to use this to get water? All right? And you can see it's about 1 meter long. All right? So this might help you if the cliff is going to be a bit further away. So let's just pluck off the leaf. All right? And see how this is going to work. I hope it works. Well, let's try this again. There's a stream of water. Is there water there? Right. Well, at least that amount will be enough to keep you alive for the next few minutes or few hours before you find the rest of your friends. Don't go away. Hang on. Now I need more volunteers there. So if I could have a few more girls to come down quickly. Now what I'm trying to show here is surface tension of water. I think this is something that we have experienced, all right? We experience this every day in our lives. And we know that insects are able to walk on water, and that's because water molecules are polar molecules. And we're going to demonstrate to you what polar molecules mean. All right, let's imagine this is one water molecule. These two are the hydrogen atoms, and that's oxygen. You have another water molecule here. All right? And the hydrogen atom is on top of... The reason why I'm doing that is because they're polar molecules. It's a positive ion. It's attracted to... You can stand up, it's all right. Relax. You just have to lift your hand up here. And we have the next person here. All right, that's right, getting it right. Okay, so this is what happens when water flows. When water flows, you make sure you grab her hair. All right, so the whole stream of water molecules is going to come together. And this is how it works, because water molecules are cohesive. All right, they're attracted to one another, and that's how surface tension works. Thank you.
Any questions for Mrs. Sundari?
Could you give examples of surface tension of water?
Well, there are lots of examples. I don't know whether you have gone to the doctor sometimes. And sorry, I'm not using a mic. And if you want to test blood, what they will do is they will use a very tiny capillary tube. Of course, the capillary action is partly the reason why the blood gets drawn up, but blood is also something where 90% of it is water, and because water is adhesive, you would see that the stream of blood actually gets pulled into the capillary tube. I mean, it looks amazing, right? But Actually, it's all to do with surface tension. Transpiration is another process. You have tall trees. How do we have water going up to the top of the tree? It's also surface tension. The stream of water gets pulled together, and that's how they reach the top of the tree. So there are lots of, applications, and water is an essential compound, and it's because of the special properties that they have that allows us to survive, all right, the plants to survive in us.
Do you have any other questions?
You have two, using the similar ingredient, you choose actually two different topics. Maybe you tell us a little bit more about making it.
Okay, making the mobile allows students to understand the simple concept of equilibrium, the principles of moments, all right? Because when you want to keep a mobile has to be balanced on all sides, and if you're going to use different items, then you've got to vary the length of the string, all right? So the brush is much heavier than the leaf. And I was actually planning to have the leaf, the brush, and the cup to be the items at the bottom of the mobile, and I was planning to make use of strings, all right, to show how students can vary the length in order to keep the mobile stable. Thank you.
Okay, good afternoon, ladies and gentlemen. What I'm going to do today will be very similar to the first presenter, Ms. Lin. Probably great mind thinks alike. That's why we have the same idea of doing air resistance and free fall. So what I have with me here is a stack of transparency, toothbrush, leaf, and a cup. So what I want to investigate is, if I were to drop these three objects, my styrofoam cup, the leaf, and the toothbrush, which one will drop faster? What do you think? Let's rank them in order of which one will drop to the ground the fastest. So the one that dropped to the ground the fastest, I'll place on my right hand side, and the one that will fall slowest, I'll put on my left hand side. So how should I place them? Toothbrush first, followed by, do you think the foam cup will fall faster than a leaf? Yes, okay. So I arrange it in this way. So let's do a simple test. Since I did not get any of my students to come here, so I'll do this myself. They couldn't come. They said that they can come tomorrow, so probably I'll meet them tomorrow. Okay, so I just compare the toothbrush and the cup. Let's put them like about the same level. Okay, clearly the toothbrush hit the table first. Then I compare the foam cup and the leaf. Oh, my leaf. Okay, so you notice that, yeah, we place them in the correct order of toothbrush, foam cup, and leaf. So we may think that, okay, probably why they fall faster is because of their mass. Okay, the toothbrush weighs much more than the foam cup, and the foam cup weighs much more than the leaf. That's why they will fall. Why they fall faster is because of their mass. But if you to investigate when there is a storm or a wind, okay, when we are carrying our umbrellas, we will find that sometimes we are being blown away. Why is that so? Okay, imagine this is my umbrella. Okay, so I will be standing under my umbrella. But when the wind blows, okay, you'll find that very often you'll be put to this side. Why? This is the idea of air resistance. That's why when I drop my cup this way and the other way, it makes a difference. The shape of the cup affects air resistance. Next, since we mentioned this thing about air resistance, then like what Ms. Lin had showed, we can reduce the effect of air resistance. One way to make the cup and the leaf fall at the same rate, we put the leaf in the cup and we drop it. You can't really see, okay? So you may say that probably the leaf is pressing against the side of the cup, that's why it falls together. What I have here is a very small styrofoam strip. Okay, I place it in a cup. Okay, if you were to drop them alongside each other, you'll find that. Sorry, not together. Okay. Okay. When it falls, the way it falls shows that there's something resisting it. Okay, as compared to the cup. So if I were to place it inside and drop, You can't really see it. Okay, but let's try with this big stack of transparency that I have here. You all have already seen this. Okay, clearly you expect the leaf to fall at the same rate as the transparencies. But if you use this small little styrofoam strip and place it in the center and you drop, okay, will you expect to see the same thing? Okay, I think so. It flew off. Okay, let's try it again. Okay, what's the purpose of doing this? Okay, I will discuss this later. Okay, you find that it dropped at the same rate, then it just fly away because of the air current that's generated. Okay, the reason is when things fall, okay, they are subjected to air resistance. But if I can reduce the air resistance, okay, by placing the styrofoam strip on the transparency, when these two objects fall, the transparency will overcome the air resistance. So your styrofoam strip does not encounter as much air resistance and they will fall at the same rate. Which is to say, if I can totally eliminate all air resistance, that is in vacuum, then you will expect these two objects to fall at the same rate. Yeah. So, thank you.
Questions for Mr. Tan?
Yeah, questions.
Would you like to tell us how you're going to do next one?
Oh, yeah, I wanted to do that, but I was I tried it and I thought that it might fail me, so I decided not to do it. Okay, this is about pressure, also about air pressure. Okay, what I wanted to demonstrate is the effects of air pressure, high pressure and low pressure, how it brings about a force. And there are three ways you can increase air pressure or change the pressure to bring about a force. Okay? One way is to use this cup. You blow into the cup. It's like pumping air into a tire. You find that the more air you try to push into the cup, the greater the pressure. So I will do it like I try blowing into the cup and you see my whole face turn red because I cannot blow anymore. Okay? That is by compression. I can increase the air pressure. The other way is I can make a very small hole in the bottom of the cup. Okay? And I am able to lift up things like this by blowing. By suction. By sucking, not blowing. Okay? And when I suck up the air, I actually create a region of low pressure. Over here, there's high pressure and it actually props the lift up. But there's something more counterintuitive. I can actually blow into the cup, okay, and be able to lift up objects like probably, this is the part that I am taking a risk. It may not work. Okay? So what I do is, take this piece of paper and I blow into the cup. You have to observe very carefully. So you notice that it actually stays, I can't hold my breath that long. Yeah, so it will actually levitate. And why is this so? It's because of Bernoulli's principle. When when the fluid is flowing fast, they will create a region of low pressure. So instead, we would think that when we blow down, it actually goes down, but it doesn't. Okay, it actually comes up because of pressure. And that is why on the MRT station, we have the yellow line. That's not, the reason why they ask you to stand behind the yellow line is not because they are afraid that the passengers that come out will stampede and crush you, but because if you stand too close, when the train comes into the station and it moves very fast, there will be a region around the train whereby you have high velocity of your air. That will create a low pressure region that will pull you towards the train, and you don't want that happening to you. Okay? And that's the reason why there is the yellow line. Yeah. So that's the entire idea.
Mr. Tan is our last contestant for today. Now the judges will Thank you all contestants. It's been a wonderful presentation today. We learned a lot. Now judges will now deliberate for the results. And for the rest of you, you will have your recess. Okay? Refreshments are outside. Please be back in about 20 minutes time. So by 3:35 or 3:30.
Okay, welcome back everyone. Now, we'd like to invite Prof. Lim, who will represent our panel of judges, say a few words about our presentations today.
Well, being the thorn among the roses, I've got no choice but being pushed out here to represent the panel of judges to share some observation. Now, first of all, we must congratulate all the teachers, participants for your courage. Certainly, we see that you're very brave to take on this challenge, and we admire your passion, the whole enthusiasm and the conviction of really wanting to bring across ideas through your creative way of teaching come across very vividly, and we're very impressed with that. And certainly we see the way you make use of everyday items, very, very common items, and yet you can bring out the science, the concepts behind all this, and we are just talking among ourselves that what if we let students play with anything like this? I'm sure the class can also be very engaging and very fun. So on the whole, we are very impressed, and in fact among our panel judges we have master's teachers in MOE, and she said that she might go back to MOE and probably look at more of such applications to promote using very common, seemingly mundane things to bring out very exciting and interesting science concepts. We enjoy ourselves thoroughly, and we have deliberated and we decided not to say who will be in the run for tomorrow, because I think all of you deserve to be considered in a total package, right? Although in a way some of you took the risk of doing things which are more risky than the rest. So in a particular case, we saw that, but we admired the sheer determination. I mean, it's really very determined to try to work. But somehow it was unfortunate. Okay. We were just wondering why did you try out with the leaves that you tried before? I mean, you used the new bunch of leaves. But anyway, that goes to show that in class when you try out something new, probably you have to practice before, or even the materials count. Right? And we also see that teachers are really good storytellers. I mean, we enjoy all the storytelling, and it's very engaging. And I was told that now, more and more so, even in science education, storytelling seems to be a strategy to engage students. And we could see some very beautiful demonstration of storytelling. Entertaining, and we almost wanted to find out a bit more about what's the secret behind, But we all in the deliberation, we couldn't come and ask what's the secret behind, or what's the story, the secret and all that. Now, some of you are very focused. We could see that you came, you planned, and you just want to show that in fact, and that's it, very focused. And being very focused, you deliver decisively, and that in a way also gave us the element of surprise. We were taken aback. Wow, okay, so that impact was also quite obvious if you choose to be very focused and deliberate. And some of you, of course, use props and storytelling or application to bring about some scientific concept, which in their own way are also very interesting, entertaining. But given the short time that we had here, we were a bit concerned about whether there are too many things to digest in that short 5 minutes or so. So this is probably something that you can reflect upon, or in future, should you come back for a similar competition, that 5 minutes to bring across a concept versus in that 5 minutes you bring across something more than that concept and created a bit more of a complexity, is something on the way, right? We also look at some presentation that managed to bring up the level of understanding from the very basic to a higher and deeper level. And again, that is a skill, that's an art that we we saw among some of you there. And I think that is, again, a very good sign. Because dealing with the different kind of students, some classes may have students who could think further than what we want to say. So the ability to bring up the level of thinking certainly is a very good practice. Okay, so on the whole, we are impressed, and we are just wondering if tomorrow the rest coming in may not meet what we have seen today, then we have clearly some goodness in our presence here. And we have also noted some of you for special judges nomination. In other words, you may not, if after comparing with tomorrow's contestants, you may not be among the top 3, but we have identified some of you to be of special mention. So you may be getting a special prize. Okay, so if you can, do come tomorrow and find out for yourself what kind of rewards may await you. Well, I think I've said enough. We shall not disclose what we think. Tomorrow we'll tell you. Thank you.
Thank you, Prof. Lim. And thank you to all judges for taking their time for this competition today. We'd also like to thank British Council for their contribution to this event. We look forward for future contribution from them. Now, thank you all contestants and audience for being here today. You're all invited for tomorrow's session as well as the prize giving. So have a good evening and see you tomorrow. The Iron Science Teacher Competition was inaugurated in 2005 as an activity of the International Year of Physics. The Science Centre continues to organise this event as a part of its mission to inspire science and technology, teaching and learning. With the continued acknowledgement and recognition of the Ministry of Education, we hope this annual event will become an important venue where teachers can exchange ideas on teaching science and inspiring science learning in their pupils. The winner will be pronounced the Iron Science Teacher of 2007 and will enjoy a special learning journey to the National Science Learning Centre at York in England to attend a course in science teaching and communication. This very special opportunity is generously provided by the British Council Singapore, which has also contributed souvenirs to all contestants and judges. Let us show our appreciation to the British Council for the generous support. Please allow me now to invite our Chief Executive, Dr. Chew Tuan Cheong, to address us. Chew?
Hi, this is going to be the most boring 5 minutes of the whole afternoon. Okay, thank you very much. First of all, the judges, representative from the British Council, and student supporters, and of course, teacher contestants. I think a few years ago when I proposed this Iron Science Teacher competition, I was rather reluctant because I wasn't sure whether teachers would want to participate. But after the first installment, we realized that actually it's a very good learning experience for us all, and I think the teachers enjoyed it. So really, it has turned out to be a very good competition. And competition is actually a wrong word, because I believe all the teachers who come enjoy themselves. So it's an event. And also, many of us, including educators and other teachers, actually learn from what goes on stage. So it's becoming a very good event. I just want to add that very often in Singapore, especially for the science and engineering disciplines, verbal communication is one of the greatest problems. The reason I think is one, because maybe students in school don't get to speak up so much. Two, English is still today not truly our mother tongue, our first language. And of course, three, engineering and science contains those terms that are sometimes not easy to understand by people who are not experts. And what's worse is when you do engineering and science, you neglect things like literature, geography, and history. So, you're strong in maths, strong in calculations and analysis, but you become weaker in the experience. Okay, you have less experience in being able to express yourself. So I think an event such as the Iron Science Teacher Competition gives everybody a lot of chance to try out their skills and the spoken word. The spoken word is the most powerful, even till today, compared to the written word or whatever you have. Give the teachers a chance to try themselves out, give the students to see what is possible, and generally give all of us a chance to enjoy ourselves. So finally, I want to echo the thanks of Charlene to British Council, as well as to the judges who has taken so much time in order to find ourselves a winner that we can send overseas to project our science teachers. So thanks once again for being here. I wish you all a very enjoyable afternoon ahead. Thank you.
Thank you, Dr. Chiu. Let me now introduce our distinguished panel of judges. We have Associate Professor Lim Tit Ning, Assistant Chief Executive Education Programs of the Singapore Science Centre, and also the Vice Dean of Science, National University of Singapore. Associate Professor Christine Chin Hui Lee, Natural Sciences and Science Education Academic Group, NIE. Dr. Charles Chu, Teaching Fellow, Natural Sciences and Science Education Academic Group, NIE. Ms. Eileen Tan, Regional Coordinator, British Council, Singapore. Ms. Nora Teo, Master Teacher, Entry Cluster, Schools Division, Ministry of Education. Let us show our appreciation for their key interest in our event. Before the contest begins proper, let me briefly explain the rules. As mentioned before, the contest is open to all teachers in all local and international schools, to the training teachers of the National Institute of Education, NIE, and to all academic staff of all institutes of technical education. Contestants need not be science teachers, but they must give a short lesson demonstration on a science topic of their choosing. Each presentation must be in English. So what is special about the Iron Science competition? Contestants must create a captivating lesson based on the items in a list of secret ingredients which were made known to them only a week ago. Another set of items only made known to the contestants this afternoon is also available for their use. Thus, all the material they use in their lesson demonstrations are provided for, and they cannot over-prepare. They cannot make training or teaching aids. Their lessons and lesson planning are thus impromptu. A list of ideas or lesson plans taught up by each contestant will be shown on the screen. Each contestant selects and presents only one of the topics. However, the audience and the judges may ask questions on the presentation and or any of the listed topics. Each contestant has 1 minute to set up, immediately followed by a total of 6 minutes to present and to field any questions from the audience, from the judges and you, the audience. We advise the contestants to finish their presentation within 4 minutes to leave more time for Q&A, as the effect of their presentation on the audience is an important consideration in the judging process. We therefore encourage you to ask questions during the Q&A period. It is important to give feedback to the teacher who is also learning. The significant minutes are marked by the shocking sound of the tap of the bell. The first bell marks the start of their presentation. The next bells will be sounded at 4 minutes and 5 minutes into the presentation. Double rings are lastly sounded at the 6th minute. The contestant must end his presentation immediately and vacate the front of the auditorium. There will be a short 15 to 20 minute recess at around 3:30, and refreshments will be provided just outside the auditorium. After all the contestants of this session have shown us their best, the judges will retire to deliberate for about 20 to 30 minutes. The judges will comment on the performances in general before the end of the day's sessions. Before the fun begins, the secret ingredients announced a week ago are a foam cup on the table, okay, a wire clothes hanger, a toothbrush, and leaves. So without further ado, let us call our first contestant. And we have with us Mr. Muhammad Malik from Kranji Secondary School.
Hi everyone. I'm Mr. Malik. I'm a physics teacher from Kranji Secondary School. Now, right here I have a styrofoam cup, an ordinary styrofoam cup given by the organizer, nothing unusual. But with this styrofoam cup, I can do some amazing stuff, probably unbelievable stuff. Okay, what I'm going to do is, I'm going to roll out. Okay, this styrofoam cup got numbers written on it, 1, 2, 3, and 4, as you can see. Alright, now what I'm going to do, I'm going to roll it on this tabletop. Alright, but before I roll, I need one of you to pick one number, which you think will face down when this styrofoam cup comes to a stop. Okay? Right. Okay, we have a good volunteer. What number would you like to? Which number you think will face downward? Number 3. Okay. Alright. Before I do the trick, he has to do something first. Alright. He has to say number 3 into the cup. It is important, or it won't work. Okay.
The 3.
Okay. Perfect, isn't it? Nice. Okay, so remember he chose number 3. Okay, number 3, huh? Remember, number 3. So what I'm going to do, I'm going to roll it, and number 3 is going to face down. Alright, I'm going to make it face down. No, not me. All of you are going to make it face down. Okay, what I'm going to do first, I'm going to use my mental. Here, sit number 3 inside. So, one magic already inside the cup. Now I'm going to use my mental power now to make the number 3 face down. Okay? Alright, I'm going to use my mental power, huh? Okay, here we go. Number 3. Number 3. Number 3. Number 3, please. Number 3. Number 3. Okay. I said my mantra, my magic mantra. Now, what I need all of you to do now is to use your, I need your help now. I really, really need your help. I want you to I want your collective mental power now to make this number 3 face down. You think you can help me with that? Thank you. Okay, what I want you to do is when I roll it, all you have to do is, okay, a bit nervous. You have to shout, number 3, number 3, number 3. Can you do that? Until it stops. Can or not? This corner. Cannot, please help. It won't work if you don't shout. It needs your help. Okay, one more time. Huh? I say the magic mantra again. Number 3, number 3, number 3, number 3. Okay, all of you ready? Yeah. Okay, here we go. Are we ready? Yeah. Okay, let's go. Alright, number 3, number 3, number 3. Okay, sorry. The table not big enough. Okay, let's try one more time. Okay, one more time. Number 3, please don't fall this time. Please stay on the table. Okay. Alright, ready? You ready? Okay. Here we go. Number 3, number 3. I think I better throw over here. Okay, one more time. Number 3, please don't fall this time. Please, one last time. Okay, we have no time. Okay, ready? Number 3.
Number 3.
Number 3, number 3, number 3, number 3. Okay. Okay, let's see whether it's really number 3. Okay, I'll watch out. What number is it? Number 3, right? Oh, man, you are really very lucky. Don't forget, I'll send you by 40. Alright, now, so it stopped at number 3. Alright, maybe you think it's a... Oh, 4 minutes already. Oh God. Okay, now let's go into the explanation. Okay, now this is not magic. What he said, number 1 inside there is bullshit. When you stop number 3, it's also bullshit. When I rub on my head, it's also bullshit. Alright? Why this thing happened is pure magic. Not pure magic, pure science. Pure science. Now anyone can tell me why number 3 is stuck here? Static electricity. Okay, that's right, that's right. Static electricity. What happened? The trick behind this trigger is to rub with your hand. When you rub, now he choose number 3, so I rub at number 3. When I rub at number 3, I create charges here, static charges. There are 2 types of charges, positive and negative charge. Right. Any charges will attract to any neutral dry surface, like this one. So there you are, see? Can you see that? You get attracted to number 3. Prove my point further. Okay, watch what happened when I put on this surface. See? When you rub, you can see your hands there. True, right? Alright. So, make it even further. Any light object can be attracted also. Okay. Now watch what happened. I hope it works. Can you see? So all these got to do it. Okay, what's the important thing is to learn with the concept. Okay, what did I say just now? Static charges will attract to any neutral surface. Got time? Okay. Now what you have just seen is static charges attract. Can static charges repel? Yes. Okay, let's demonstrate. Now I got 2 charges. It can repel. Okay, first I got to rub in my hand. This one I'm going to create a lot of charges on both cards. Okay, now I have what charges now? Similar type of charges. Okay, now let's see whether it repel or not. Watch out. I hope it does. Alright, can you see that? So, when you same charges placed near together, they attract. So, let me sum up. Charges attract any surface. Okay, that's it. Thank you very much.
Our next contestant is Mr. Lam Chi Meng from Pioneer Junior College.
Good afternoon. This T-shirt was given 3 years ago at the first session, and I haven't washed it since. I like it. Anyway, today we're going to talk about teaching of pressure with pleasure. Okay? Have fun. Now, if you go to a costume party and you want to put on the nose of a pig, okay? Here the pig, for example. If you don't have super glue, what you can do is just suck. Okay? Yeah. So the question is, assistant, where's my assistant? Now, why is it that when I suck, it sticks on? I created a, start with V, created a V, a vacuum, okay, thank you. So the air pressure, although it's air, but it's 5 kilometers of air, has tremendous effect. Now let's do some tricks. Anti-gravity trick, okay, nothing special, just a normal cup. Okay, just to show that there's water, I didn't love you, I didn't pour on the water, okay. Now water you pour over, likely will spill, right? Let's see how we can have anti-gravity property, okay. Correct word is incredible. That's it. Harry Potter. Let's see whether it works or not. There you are. I didn't block you are. Now to make it ungravity, go back to normal. I say Harry Potter. Now what did I do? Why is it that I say Harry Potter, thing drop? Why? What did I do? What did I do? Yes, correct. Thanks. I take out the finger and air goes inside, okay? It was a vacuum because I inverted it, there's a gap there. And the air pressure can actually, in theory, give me 10 meters of water high, okay? Right? Magic with pressure. Now, remember the pig, the wolf who blew up, huff and puff, huff and puff. You can't do it, right? Now, the fairy tale didn't tell you his secret, it was not written, but the trick was he used increased pressure. How? He used his tube, he huffed and he puffed and he, there you are. This tube, you concentrating the pressure, more pressure, greater force. Got it? So pressure can do marvelous things if you know how to do it. Now, you're all hardworking girls, very few boys here. Now, sometimes you're under stress, okay, very sad. You lost the pressure of, now, the pressure is defined as force over area, okay? Now this chap is very burdened with heavy burdens of pressure. It's quite scary, you know. Please don't do that to yourself. Now, what I suggest you have friends. Okay, good that you have a lot of friends. That you're a happy guy, you know. That's not a gloomy, not happy guy. With friends, you can share the same force. Your mountain will never grow bigger. It will be the same mountain. The force is the same, but the pressure is smaller because you have bigger area. With more friends, you can share your burden. They're still smiling. So please be happy and life will be great. Thank you. Any questions on the topic?
We have some time to take some questions from Mr. Lam.
Any questions? Yeah, I thought I'd just focus on one topic. Because a lot of pleasure playing the pressure. So much fun that I couldn't think anything else. But in a science lesson, normally we only one topic. We don't teach 4 or 5 topics. So we try the one lesson, different way of teaching. Well, the toothbrush was given, and the tube was given just now. Tube was given.
So if you use a leaf to illustrate.
Leaf pressure. Actually, there was an idea of balloon, a small little bubble, and use if I hit it, normally you won't break a sharp end, you break it. That was the idea, but I didn't go through.
Okay, any more questions? Okay, thank you, Mr.
Right, thanks.
Our next contestant is Miss Tay Chun Yan from ITE College West, Bukit Batok. Miss Tay?
Hello, good afternoon everyone. Today I'm going to demonstrate to you how to determine the density of an object. How is it determined? Density. So in fact, density can be determined by, have you learned density before? Density is related to mass and volume. Hence, today I'm going to demonstrate to you using a clothes hanger and compare the masses of a piece of leaf and a 50-cent coins. So now, this phone card will empty. Firstly, I balance it first. The toothbrush to support. Now, which one do you think will be denser? Is it the coin or the leaf? Okay, let's test it out. So I'll put a leaf on one side and a 50-cent coin on the other side. So obviously, the coin is denser. Am I right? Because it tilts small than the other end. So look at this mass, this 50-cent coins. Okay. Although it's heavier than a piece of leaf, but the volume is smaller. So how can we relate this to density? So if a volume, this coin has a smaller volume, your density will be higher. And therefore, from this equation here, it can tell us that density is directly proportional to mass and inversely proportional to volume. So do you have any question about this demonstration? Yes.
What has density to do with floating?
Floating.
Yeah, flotation.
Rotation. From what I can see from this equation, do not think that rotation has to do with the density, because purely density is actually dependent on your mass and the volume. So if you have a big, denser, if your mass object is denser and have a smaller volume, then your density will be higher. Anyone else? Yes?
Are we assuming that the mass of the coin and that of the leaf are exactly the same?
No, definitely no. Unless I'm comparing two types of leaf and the mass are having the same mass, okay, but the the volume is different, then we can conclude that even though you have the same mass, okay, but the volume may not be the same. So, then it comes to this equation again. The higher the mass, the lower the volume, the density will be higher. Thank you.
Next up, we have Mr. Darren Tan from Pioneer Junior College.
Alright. Okay, first of all, welcome to the wacky world of physics. Now, what I have here is just two conical flasks, right? They are just really heavy glass pieces. And this here, in blue, is a wire hanger that I've cut open and twisted into this shape. Alright, I've secured one end with string and the other end with string as well. What I'm going to do is actually show you that I can balance this on my cap. Alright, this is my alien head here. I turn around, but it doesn't turn. Right? It turns a little, but very little. Right, see, if I put it at rest first, and then I start turning. The flask does not turn. I turn, but the flask does not turn. Now, there are a lot of physics going on here. Let me just try to explain some of it. First thing is Newton's first law. Newton's first law is really very simple. First law. Right? Object at rest stays at rest, or to be more accurate, tends to stay at rest. What does this mean? These heavy flasks, right, they are on top of my head, but if nothing pushes them around, right, they will just stay there. I might be moving, the world might be moving, but they just stay there. Alright, so that's Newton's first law, sorry. First law, objects at rest, stay at rest. But I think the more interesting question that you have is, how did I manage to balance the two flasks on the top of my head? For that, let me take this off first, because this is what I'm going to use to explain. Now look, if I balance this cup from my finger, it's so easy, right? The cup doesn't fall down, it just stays there. But look what happens if I try to balance the cup on my finger but from underneath. It's really quite impossible. So likewise, right? When I'm balancing the two flasks on my head, look where most of the mass is. Right? The most of the mass comes from the heavy flask, and that's below the suspension point. It's exactly the same as this situation, where most of the cup is underneath my finger. So, draw a diagram. Right? Imagine an object like this. If I suspend it with a string from here, right, let's say the center of gravity is around here. When I move the object a little bit, right, the center of gravity moves upwards. Right, see the cup? When I move it to the side, the center of gravity moves upwards along with it. You know, center of gravity actually likes to come down. Things like to fall down. When I let go of this cup, it falls down. So it tends to go back to its original position, so that's why we call it stable. The opposite of this would be something unstable. Let's say I try to balance the cup on top of my finger here, like this. right? If the center of gravity is here, if the cup moves a little bit, right, the center of gravity moves downwards. And because things like to move down, when it moves down, it keeps on moving down, and so it falls. So this is really the explanation of why things are stable when they are stable and things are unstable when they are stable. It's about energy, it's about center of gravity, all very cool stuff that you get to learn when you study physics. So I think at this point I'll open the floor to questions about any of this stuff. Right, anyone want to try balancing this on your head? It's very stable. Right? Even though it's made of glass, I'm not worried. I'm not saying, oh, can you have some supporters here in case it falls and it breaks? Right? I'm not worried at all. Any questions? Yes? Okay, where's the center of gravity for this headgear? Actually, from the drawing, right, you know that whenever I have something that is suspended, the center of gravity is always in a vertical line together with the suspension point. So I would think that the center of gravity, okay, it definitely has to lie along this line. So if you drop a string vertically downwards, it's somewhere along the line. Because most of the mass is in the glass, right? If we consider separately, one glass, the center of mass is around the center of this. The other one, the center is around the center here. The center for both would be in between the two glasses, the two glass beakers. So I would estimate that the center of gravity is roughly here. Well, you can actually do this with just a clothes hanger and any two heavy objects. It doesn't have to be glass. Ideally, you would use plasticine or something that you can find easily at home. Something heavy, just put it here, wear around, show your parents, show your friends. You have a good time doing physics. Alright, thank you so much.
Thank you, Mr. Darren Tan. Our next contestant is Mr. Tan Boon Kian from Nanyang Girls High School.
Welcome to organizers, judges, ladies and gentlemen, boys and girls, Today my lesson is on making sound, right? Right now I'm speaking quite softly compared to the other teachers. Because, well, I'm not making loud sound that you can hear. So what is the principle? How to make sound, right? How to make sound? Anybody, any girls can answer this question? What do you need to make sound? How is sound produced? Anybody? Yes? Vibration, very good. Vibration. Okay, I believe when you are young, you see performance on stage, on television, and they strum guitars and everything, right? And I think some of you will have this urge to make your own guitar, right? And I have here make something like that when you were young. You like to make something like that and can strum along, right? I want to invite all of you to come down and see whether this one can work, alright? Any girls to come down to try whether this can work? Anybody? Anybody? Thank you very much. Okay, so this make a sound using this. What do you do? I hold it for you. You will talk on it, right? Okay. Not very loud. Let's bring near to the mic here now. Right, harder. Okay, thank you very much. Doesn't work very well. Sorry. I failed well, right? Okay, it's my fault. So, so you know that vibration is causing sound to produce, right? So a vibration like a hanger, right? Not loud enough. So not loud enough, right? How do we make it louder, right? To make it louder, maybe I can have some magic here, right? The name of magic actually is science, right? Just attach this styrofoam cup to the hanger, right? And do the same thing now, right? doesn't sing that well, right? Okay, okay, you feel like you change it a bit louder, right? Now there's a reason for why this thing is making louder, right? Okay, without this cup over here, right, with the cup attached to it over here, again, right? Now the same thing here. This is some guitar that some string instrument they make when you're young, right? So everyone try it, right? See whether it will make a louder sound, right? Then the ladies come down again to try whether it works. Okay, do the same thing here, right? Just do what you did just now, same way. Try again. Right, thank you very much. Does it make it louder? Right. Now this principle that you use here, maybe you go home and try to do the same thing and see what is the way to make it louder. Right. In fact, this principle is used in every instrument. And what you are doing here is that we are attaching the styrofoam cup. We are making something called the. Anybody can tell me? Not really an amplifier, but something close to it. This thing allows the sound to be amplified louder, right? What I have here is actually produce something called a sound box. And you find that every instrument, like guitar itself, you find the guitar, right? It's just the string here. What you have is a sound that is not very loud, right? But if the guitar, behind the guitar there's a sound box. And this sound box, what happens is that now, why is the sound not loud enough? Because the string itself, the vibration of the string produces vibration in the air. And the vibration in the air, because the string is very small, right? The volume of air that produces vibration is very little, right? Now what happens is that you have sound box attached to it. What is the instrument now? Is the instrument is attached to the ruler itself, here. Then the instrument will cause the string once vibrates will cause the instrument, the rule here to vibrate. And this rule when it vibrates, will attach to the this styrofoam cup, will cause the sound of the styrofoam cup to vibrate at the same frequency as well. Right? Same way, they vibrate the same way. So when it vibrates, it produces more sound to vibrate, and then you can hear a louder sound. Right? Any question? Boys and girls? Ladies and gentlemen?
Okay, thank you very much, Mr. Tan. Contestant is Madam Shalina Low from NIE.
Okay, good morning. Good afternoon. Okay. Today I'm going to talk about forces. Now, forces are everywhere. Do you believe that? May the force be with you. Now, forces are everywhere. Now, before I start on forces, what do you think? How do you think I will put force on this? Anyone? Now, I will continue to talk about it. I want you to take a look at my items for a while. Okay, take a look and then pass it around. Okay. Okay, now forces are everywhere. It is up to us as scientists to look at it and find out what are the characteristics of forces so that we can harness the energy. Now, I have this. Now, who's holding this? Who's holding the other one? Who's holding the other one? Stand up. Those who are holding. Okay, now stand here. You be my target.
throwing out? Can you throw a ball? Don't worry. Okay, now I want you to try to hit this. Okay? Like this. Twirl it around. And then you're left-handed or right-handed? Right. Okay, you stand this side. Okay? I want you to do it this way and let go and try and hit this. Okay, for the rest of you. Okay, for the rest of you, I want you to see when she lets go. Okay? Okay, try again. Ready? Sing harder. Okay. Okay, it's okay, it's okay. Okay, now this, yeah, sit down first. Okay, this is actually, we are using centrifugal force. Okay, this is an adaptation of the sling, which is one of the weapons they had used a long time ago to kill small animals for food. Okay, so they are using centrifugal force. Now, for my second experiment, how can you adapt this centrifugal force to move this toothbrush up without touching the toothbrushes? Can you think of anything? Okay, swing has to do with swinging. Swing. Okay, thank you. Okay, so this is another way to harness the energy of centrifugal force. Okay, to pull something up. Now, why would we want to use centrifugal force? And one more thing. Okay, this holds what? What do you think? Is there a cup? Okay, this holds ice water. This holds ice water. You bring extra clothes or not? Ready? I better not wet the judges. I can wet you, right? Okay, ready? Ready? Okay. This is also centrifugal force. But why will we want to use centrifugal force? Why will we want to use that? Okay, right now, in space, those of you who have watched Star Trek, do they have gravity in space? They will be floating all over the place, right? So in space, they make use of this idea, centrifugal force, in their space stations. Okay? So as I use this to hold the water inside, on the inside as I turn this, okay? As the space station turns, everyone will be able to walk on the outside of the rim, just as if they have a gravitational force. Okay? Now, I'll open the floor to questions.
Do we have any questions? Yes, there's one up there.
What's the difference between centripetal force and centrifugal force?
Oh, centrifugal force, sorry. Okay, centrifugal force is actually using something to stir.
Thank you very much. Our next contestant is Mr. Tan Yin Soo from ACJC.
Alright, so before I begin, a little bit of a preamble, right? This lesson I'm going to show you is suitable for both secondary school and junior college students, but just for the purposes of this lesson, let's assume that this is an enrichment lesson for JC1 students. Alright, I've always been very fascinated by this thing called a ping pong ball. I mean, look at how lightweight it is, how bouncy, alright, and how, just using my breath, I can actually push it around. Alright? Okay,
So if I combine this ping pong ball with a styrofoam cup, we're going to see something very interesting about pressure and forces, right? Okay, but first, I'll need 2 volunteers. So how about can I have the gentleman in the black shirt and the friend right to his right? Okay, thank you very much. Alright, and the rest of you stand right next to me here, please. Okay, this is Hafiz and Izzat, right? Alright, okay, so have you heard of the movie The Narnia Chronicles? Okay, so I have a piece of bad news for you. The both of you have been kidnapped, okay, not by the White Witch, but by the Black Wizard, which is me because I'm all dressed in black. Alright, so the both of you look like you have very strong lungs, right? You have very strong lungs. Okay, so this is what I need you to do for me, alright? I'm gonna give each of you a cup, alright, with a hole at the bottom. So can you do something for me? Just blow through the hole like that. Oh yes, they have very strong lungs. Okay, so now this is my next challenge to you, right? If you can pass this challenge, I'll release the both of you. If not, you'll be trapped in my castle for until 6 o'clock. Alright? So now I'm going to give you a ping pong ball. Alright? Now, okay, here's the challenge. Alright? Don't do anything first, huh? Okay? So this is what I want you to do, alright? I want you to blow through this hole. Do first. Blow through this hole as hard as you can, and let's see if you can blow the ping pong ball out of the cup or not. Alright, just hold this vertically upwards and blow as hard as you can like that. Yeah, do it vertically upwards, please. Okay, and do it as hard as you can. Okay, on this, can you cheer him on? Alright? Okay, thank you very much. Okay, so as you can see, no matter how hard they blow, right, they are unable to get the ping pong ball out of the hole. Okay, so now, since Hafiz has a stronger build, right, I can see his muscles and things like that, I'm gonna make things a bit easier for him. Alright, so instead of asking him to blow this vertically upwards, right, so Hafiz, can you blow it horizontally like this? Okay, okay, when I say at my count of 3, 1, 2, 3, okay, but then judges, don't worry, I have confidence in my physics, alright? 1, 2, 3, blow. Okay? Okay, so, okay, can I give these 2 gentlemen a round of applause? Okay, thank you very much. Alright, so now I'll show you what is the right way of getting the ping pong ball out of the cups, alright? Let's see. Okay, I guess you can do it all and all, right? Alright, thank you very much. Okay, so now the question is, okay, because you are JC1 students, right, what is the concept, what is the physics behind it? Okay, it just so happens that a gentleman named Bernoulli, right, he figured out this concept many years ago. It is known as Bernoulli's principle, alright? So essentially, Bernoulli's principle says that when air moves faster, okay, its pressure drops. Alright? When air moves faster, its pressure drops. So what happens is that in the first situation where I got Hafiz and Izzat to demonstrate to me, right, no matter how hard they blew, like, right? So what's happening here? So assume that this is the cup, right? And the ping pong ball is here, alright? So can we look at this situation here? When my airflow is from through the bottom of the cup, right? Alright, the speed of the air that is below the ping pong ball is slower. Okay, so what happens is that we are actually creating a low pressure region here, right? And similarly, but the air above the ping pong ball is still at a higher pressure. So now let me ask you, what happens when there is a difference in pressure? What is produced? Anyone? Okay, when there is a difference in pressure, right? Because this is at a higher pressure and this is at a lower pressure, the net force acts downwards. And this is why, right, no matter how hard they blew, they're unable to extract the ball. Not only when they are unable to extract the ball, they've actually made the ping pong ball sink in even deeper. So then how would you explain this case? Okay? It is just the opposite. This is at a low pressure and this is at a high pressure and the net force acts upwards. Alright, okay, thank you very much. Any questions about the physics behind this? Thank you very much. Okay, if not, no question, maybe I can ask you a question, right? What are some of the practical applications of the Bernoulli's principle? How about the gentleman that is in the black shirt? Yeah. What are some of the practical? Yeah, it's you. Some of the practical applications of this.
Vacuum.
All right. Okay, not so bad. Vacuum. Vacuum. Okay. Anyway. Okay. Bernoulli's principle is what keeps birds in the sky and airplanes flying, right? Okay. When your wings are tilted, so when air moves across the upper part of the wings, right, they move at a higher velocity. So as a result, the difference in that produces a lift. All right. Thank you very much.
Thank you, Mr. Clark. Next, we have Ms. Junaida from Paya Lebar.
Okay, before I begin, I need a prop, my girl. Judith, come down. Because she's quite tall, she's one of my taller girls. And I noticed that there's nothing to hang this thing on. Finger. Extend your finger. Stay. Okay, now let's begin. Now, I'm not going to say what the lesson is about, although you can see it up there, but you can see that obviously something is not balanced down here. And in primary school science, it's very difficult to introduce things like Bernoulli's principle, particulate nature of matter, and all those things that we've learned when you go up further from primary school. You need to downsize all this into digested bits for the children to understand and to make it easy for them to understand science concepts without putting them off from science forever. Yeah. So the thing is, what can I do to make sure that this thing will balance? What's the simplest thing? Anyone? Just add something of equal mass. Yes. So that is one thing in our science syllabus, mass and volume. Nothing, no density in primary school, sadly. So what can I do here? I'll just tie it down here, a bundle of leaves. And what do you see? Somehow or other it balances, which means that I can assume that this thing here and this thing here are of relatively equal mass. But that's not the fun of the lesson, unfortunately. Okay, I'm going to take this away now. Thank you very much. Here we go. Okay. The point is just to get rid of all the variables in science experiments. In any science experiments, to make it fair. What? How many variables must be changed, girls? And everyone else? One. They all know it. It's a mantra. They must know to prepare for their PSLE. They must know there's only one variable change to make any experiment, be it from primary school science to university level science, one variable only. So now let's just test this. If I drop this at the same time, okay, assuming that the mass is already the same, which one will reach first? Or will it be equal? Okay, let's just say I hear murmurs of equal, so I'll just drop it out. Relatively, reach the ground at the same time. Okay, but what if I decide to change one of the variables here? Okay, I'm not being environmental unfriendly, okay? Because the leaves are already plucked. Yes. Green award. We need to make sure that we are environmentally friendly. I'll just shred all these things. So little you guys help me get out. Okay. I'm going to drop it now. Mass is still the same. Relatively still the same. So which one will reach first? Okay. Who says here? Raise of hands. It's okay to be wrong, it's okay to be right. Which one? This one, who says this one will reach first? Okay, let's try. Okay, you can see that the last leaf takes quite some time to fall. Okay, and why is this so? It's because of air resistance. Unfortunately, again, I cannot introduce this in the primary school syllabus. A lot of restrictions in there. Okay, let's just think about it. I have a foam block. Pardon my drawing. I'm not gifted in art, unfortunately. Okay, and I have leaves, small surface area of leaf, which was previously one huge clump. Basically, the surface area here and the surface area here are kind of equal. So the variables are the same, and the air resistance and the gravity acting from the ground, and the force acting is equal.
But once I crumpled it, I have divided all this clump into smaller bits. Therefore, the surface area is less, which means there is less acting, force acting. Therefore, it will definitely be less air resistance, causing a longer time for the leaves to go to reach the ground. So in other words, I'm also testing out Newton's third principle, which is for every force there's an equal opposing force acting on it. So basically, that is the concept. Thank you very much.
Our last contestant before the recess break is Miss Nisha Kauman.
Good afternoon to everyone. Before I start off, I think some of you must be feeling that how come she's just coming here with just one item. Actually, I was thinking since this is the iron science competition, I was thinking of just using an alloy of iron. So it's steel, making use of a hanger. Alright, today I'm going to discuss a little bit about materials. Now, how many of you, by your show of hands, actually feel that a metal, or a material, actually not metal, a material that can be bent is weaker than a material that can't be bent? I repeat, how many of you feel that a material that can be bent is weaker than a material that can't be bent? Okay, so a few of you feel that a material that can be bent is actually weaker than a material that can't be bent. Okay, in my presentation today, I will actually try to dispel this misconception that some people have regarding material. Now, I would like, using a hanger, I'll try and dispel that misconception. Now, I'd like to get someone strong to come here and try and bend this, okay, Sylvia, come. Get you to try and bend this part of the wire, okay, bend it and try and restore it to its original shape, okay, just this portion here, okay, bend it as hard as you can, okay, now try and restore it, can't, okay, you're trying, okay, bend it again, now try and restore it. Bend it again. Okay, try to restore it. Are you feeling, how do you feel? Don't know how to do. Getting tougher? Is it more difficult? Yes. Okay, thank you. Alright, you can tell that, she's having a lot of problems actually trying to restore it in its original shape with repeated bending. Now, what exactly is happening is that the more she's bending this, it's actually becoming stronger. Okay, now why is this happening? I'm going to demonstrate this using a few students to come here. Alright, can I get a few students? Alright, just about 5 of you. Okay, now in the primary school level, like what Mr. Schneider mentioned, they haven't learned anything about atomic structure, atoms, molecules, so I will talk about this using the word particles. Okay, so can you hold hands? Hold one another's hands. Okay, before I had actually applied any pressure, applied any force on it, this is how the atoms are in this hanger here. Okay, this is how the iron atoms and all the other atoms in there. Alright, this is how they are. How do you feel when you're standing this way? You feel good? Okay, now what I want you to do is try to twist yourself, twist your arms, entangle yourself in whichever way you want to do it. Okay, how do you feel now? You feel comfortable? Can you move very well? Can you? No, this is exactly what is happening. Alright, the fact that we apply stress on the metal, on this metal here, the atoms, the particles in there we are actually restricting their movement. So what happens is it's very difficult for them to dislocate. And thus, in science, actually, there's this term known as strain hardening. All right, the metal actually gets its mechanical strength. So by applying this stress on the metal, they actually feel we're actually hindering their movement, hence conferring mechanical strength to the metal. All right, thank you very much. In fact, if you notice in this hanger here, the fact that this is bent, the bent portions here are actually tougher, they're actually stronger as compared to the sections that are not bent. So just to reiterate my point that I'm trying to make here about a misconception that some people have that just because certain materials can be bent doesn't mean that they are weaker. And in terms of metals, for metals actually, when they receive this force or when stress is applied to them, it actually confers mechanical strength to them through this process known as strain hardening or work hardening. Thank you very much.
Does anyone have any questions for Ms. Lisha?
Actually, because like what I said, I felt that, since this, if I would use the cup, actually I was thinking more on talking about Hooke's law. My intention was coming up with Hooke's law where I have elastic deformation, plastic deformation, and then fracture. So I was intending to show that for a styrofoam cup, you don't have plastic deformation. It's just elastic deformation and fracture. But then I was thinking that since I'm a primary school teacher, why not I do my best to explain a particular concept in a best way as possible, doing away with Hooke's law, which is a secondary school concept.
Thank you very much, Ms. Let me welcome our next contestant, Mr. Tan Beng Tai from Pioneer Junior College.
Hi, good afternoon, everybody. Okay, thank you for taking the time to come down here to witness this very exciting 2 hours event. Okay, so right now, to reward you all for effort, I'm going to give one lucky participant $50, okay? All I need is for the participant to blow a ping pong ball out of this cup using a straw, okay? Okay, anybody like to try for this $50? Any volunteers? Only one participant will be selected, only one. So, anybody like to volunteer? It's okay, got nothing to lose. Okay, you can blow it up this way, vertically, then the money is yours. Okay. It seems like it is rather impossible. Will a guy like to do it? A stronger guy, maybe? Any man would like to do it? Volunteers? Okay. We will leave it for now, okay? Let us try again. This time we'll try again, but with a sponge. Before that, we prepare another cup. This cup is for my own use. Yeah. For hygiene purpose. Okay, so anyway, this is also the same card as this, okay? But when you put it's actually a cut version, so you can see the ball more clearly, so that you can see there's no prank. Again, you find that it's quite impossible to blow it. Okay, I'm quite a big size person, so okay, let me try my best, okay? Okay, you find it's very difficult to blow this ball out. But let's try with another equipment. Let's try to blow, instead of a ball, a sponge. Okay. This is a square sponge. Everybody can see it? Okay, this sponge, I put it inside the cup and I blow. Okay, this sponge will come out. Okay, so let me ask you all a question first. So, students, actually I've seen that there's a sponge here, a square, and a circular ball. Okay? They behave differently. Okay, anybody like to guess why?
$50 for those who will guess correct. How about that? Anybody? Okay, let me not risk my money. Okay, just in case. Okay, I'd like to tell you all a story now. Okay, when you blow, right, there'll be air that is going up the straw. Okay, and there'll be a lot of air moving through the side of the object. Okay, in the event of a ball, there'll be very fast wind speed at left and right of the ball. A very fast speed. Very fast speed, right? It actually means low pressure. Okay, so fast speed. Okay, it's similar to Bernoulli effect. Okay, in fact, it's Bernoulli effect. Fast speed means low pressure. Okay. However, at the top here, there's no wind movement or very little wind movement. So there is low speed here. And low speed means high pressure. Okay? So okay, just to correct some of the other presenter, this is actually high pressure. Okay? So in fact, the faster you blow, the lower the pressure here and higher the pressure. And the pressure difference becomes greater. Okay? And if the pressure difference is great, what happens? What happens is that the ball is being pressed downwards into the cup. So the harder you blow, the harder it is for the ball to get up. Yes, correct. Okay? So whenever you come to this kind of case, right, I'm going to show you something that's very amazing. Oh my ball. Okay, it's no big deal. It's no big deal. Trying to blow the ball out. Okay, let me try to invert the cup this time. And I blow. Do you think the ball will remain in the cup or will it go down? Anybody think it will remain in the cup? Oh, very good. Very intelligent people. Okay, yes, correct. It will remain in the cup. Okay, let me show you. But now, it's 4 minutes, right? 1 minute. Okay, good. Okay. Wait, let me take a bigger cup just in case. Just in case. Wait. Okay, wait. Okay, I will ask the representative to come down. This guy got bigger breath control than me. Okay, can my assistant come down, please? He used to play a musical instrument, so he got very good breath control. Okay, so, ready?
For hygiene purposes,
So sorry. See the ball remain in the cup until you stop blowing. Okay, this is the magic of science. Okay, so in life, when we see things that we don't understand, we see things that we think are magic. Actually, it's not really magic. All of us just lack a little bit more knowledge to understand the world. So understanding the world requires much science, and that's why all of you should apply yourself to science studies. Thank you very much.
Thank you very much. Our last contestant for today is Lim Jin Mia from Kranji Secondary School.
Good afternoon, judges, boys and girls, colleagues. As you can see from the topic, non-electrical amplifier, so that's why there was a delay. I was wondering whether I should using electrical amplification here. And you saw that I drink water because I'm quite nervous. Good. More water for me. Okay, right now, without electrical amplification, I would like to sing you a song. Before I sing you a song, I must have rhythm. So I'm going to use this coat hanger as the rhythm, as an instrument to create the rhythm. So please pay attention. Can you hear me? You can't hear the rhythm, right? You cannot hear the rhythm. So that's a problem. Let me take a cup of drink first. I got an idea. First, I remove some part of the styrofoam cup. And this is what I do. Can you hear me? Yes, huh? To test again, can you hear me using this one to create the rhythm? Cannot, right? Okay. Okay, let me do it. I hope this will work. Can you hear me? Can you hear me also? Now I can sing the song without electrical amplification. When I hit the coat hanger, it starts to shake and vibrate. It turns it, the cup will shake, and the air around it will vibrate too. Now I know how to make the sound from very soft to very loud. Thank you very much. I'd like to thank Mr. Tan Boon Hian, earlier on has done the presentation, who has taken quite a bit of the